Imagine trying to pat your head and rub your belly, but your biological wiring actually forces you to use the exact same nerve pathway for both motions.
Yeah, one signal is inevitably just going to wash the other one out.
Right, exactly. And for years, if you've been working in embodied AI, that is exactly the structural nightmare you've been forcing onto your models. So, welcome to AI Paper Slop. This is the series where we summarize the latest AI and tech papers for researchers and engineers.
We are getting into a really fundamental solution to that exact problem today.
We're looking at a deep dive into this paper called ABot-M0.5, which is, let me get the full title, Unified Mobility and Manipulation World Action Model. It was published by the AMPF CV Lab at Alibaba Group, July 1st, 2026.
It's a massive paper.
It is. So let me give you the high-density core insight right up front. ABot-M0.5 basically unblocks the mobile manipulation bottleneck in world action models by explicitly aligning three things we normally leave completely fractured.
Temporal granularity, action space, and train test inference.
Boom. Yes. And they achieve this through three main contributions, right? First, they introduce these intermediate latent actions as a computational bridge connecting coarse video predictions to fine-grained motor torques.
Which is huge.
Right. Second, they deploy a dual-level mixture of transformers, a DMOT, to computationally decouple the base mobility from arm manipulation. And third, they have this novel training phase called dream forcing.
Dream forcing, yeah. That cures the exposure bias that causes models to collapse during those long horizon rollouts.
So if you've ever watched your robotic agent, perfectly navigate a room only to violently smash a coffee cup because the low-frequency movement gradients destroyed the high-frequency grasping weights, this is absolutely the architecture you need to unpack.
Yeah, to really understand how this architecture fixes those failures, we kind of have to look at the underlying physics of why standard vision language action models, the VLAs, you might literally be training right now, why they fail so spectacularly when juggling multiple physical tasks over time.
Over extended time frames, specifically.
Exactly. It all traces back to these structural mismatches, and the most glaring one is the temporal granularity mismatch. Because when we train a model to predict video, to, save on compute, we compress future observations into these temporal chunks.
Which, that's perfectly logical if you're building a generative video model, right?
Right, yeah.
You want macroscopic changes, a car moving down a street, or someone walking across a room over a 3-second span. But if you're an ML engineer trying to use that exact same temporal chunking to drive physical hardware,
you hit a massive wall.
Because a robot requires step-by-step, fine-grained precision at the millisecond level.
Yeah, by forcing the network to smooth out its temporal resolution into those coarse chunks, you actively erase the critical micro-moments. We are talking about the exact frame of contact onset.
The specific millisecond of grasp closure.
Right. The tiny high-frequency alignment corrections a robotic arm executes right before inserting a peg into a hole. The predictive physics just get entirely blurred out in the latent space.
Okay, but even if you manage to somehow reconstruct that temporal blur, you run into a second brutal physical reality, which takes us right back to the head patting and belly rubbing problem.
The action structure mismatch.
Yes. Moving a heavy mobile robot base across a factory floor requires this smooth, low-frequency, continuous power. But reaching out to pick up a fragile component with an end effector requires twitchy, high-frequency, contact-rich micro-adjustments.
And when you shove both of those distinct physical realities into one shared neural pathway,
one behavior just dominates the other.
Exactly. You are forcing the network to optimize completely conflicting mathematical patterns within a single set of weights. So in practice, this triggers massive gradient interference during backpropagation.
Because the high-frequency loss signals generated by the manipulation tasks are sharp and noisy, right?
Right. And they bleed over during weight updates. They actively destabilize the smoother, low-frequency gradients needed to predict the mobile base's trajectory. The network effectively fights itself during every single optimization step.
Wow. And then there is the third structural mismatch, which really rears its head when you finally take this self-conflicted model out of the simulator and try to actually deploy it.
Oh, the rollout condition mismatch.
Yeah. Anyone who has trained inverse dynamics knows the crutch of teacher forcing. We condition the model on clean, ground truth video latents drawn directly from the training dataset.
But in a real-world deployment, those clean ground truth futures do not exist. They just don't.
No.
The model has to act autoaggressively based on its own generated and inherently noisy video predictions.
So the moment the model encounters its own visual artifacts like a hallucinated shadow or a slightly drifted geometric edge, it panics.
It totally panics. It has compounding errors because the neural network was never exposed to its own noise during training. It is a textbook, fatal case of exposure bias.
Right, so we're dealing with a trifecta of failures here. A temporal gap, a spatial gradient war, and a training context mismatch. Let's look at how ABot-M0.5 tackles the temporal gap first. Because if coarse video chunks smooth out the necessary micro moments of control, the brute force engineering solution would just be rendering the predicted video frame by frame.
Yeah, but nobody has the VRAM or compute budget for that.
Obviously not.
So they avoid brute force by building a highly structured computational cascade. The flow moves from a video latent into a frame-level latent action, and then finally into the robot action.
Okay, break that down for me.
So the model first predicts the macroscopic future visual dynamics. This represents the broad evolution of the world state, capturing those low-frequency changes. But crucially, it physically prevents the model from mapping those broad visual changes directly to motor torques.
Ah, so it introduces a middle layer. Instead of going from a blurry video prediction straight to, like, move servo 4 by 12 degrees, it distills the coarse visual prediction into what they define as latent actions.
Yes. These are essentially frame-level motion intents.
They capture the local visual state transitions, like the conceptual idea of the gripper needs to close around this handle.
Exactly. And only after establishing that conceptual motion intent does the model ground the latent action into embodiment-specific low-level controls, which are the final executable actions.
I mean, as someone who builds these pipelines, my immediate reaction to adding an intermediate token layer between perception and control is honestly skepticism. I look at that and see parameter bloat.
Sure.
Doesn't introducing a massive bridging space of latent actions just explode the parameter count and latency overhead for what might be just a marginal gain in precision?
Well, it would if they use standard dense attention across all tokens. But instead, they implement a strict asymmetric information flow to make the computation highly efficient.
Oh, interesting.
Yeah. During the training phase, the future video latents are explicitly masked from attending to the latent action tokens. Which makes logical sense, right? Future motions shouldn't be accessible when you are trying to predict the broad visual future. However, the action tokens are structurally forced to explicitly attend to the latent action tokens.
So you're engineering a one-way computational dependency.
Exactly. The intermediate layer acts as a bottleneck that forces the network to mathematically separate the intent from the kinematics.
Wait, I love that.
Yeah, the embodiment-agnostic physical priors. So the core understanding of how objects move and interact visually are isolated within that latent action space. The hardware-specific kinematics, how a specific robot arm fires its motors to achieve that interaction, are isolated in the final translation to executable actions.
Which means if I swap out my robotic arm for a completely different model, I shouldn't have to retrain the AI's underlying understanding of physics and object manipulation.
Not at all.
The latent action dictating turn the dial clockwise remains mathematically identical. I just need to adapt the final layer to map that conceptual intent to a new set of hardware servos.
Right. It makes the architecture vastly more adaptable to diverse physical embodiments, which honestly is the only way we scale robotics beyond single-use laboratory setups.
Okay, that bridges the temporal gap without blowing up our compute. But we still have to fix the gradient interference problem. We still have the high-frequency manipulation gradients actively fighting the low-frequency mobility gradients.
Right.
To solve this, the AMPCV lab introduces the dual-level mixture of transformers, or DMOT. Walk us through how Level 1 fundamentally separates the modalities.
Sure. So Level 1 is the modal level MT. The goal here is basically to prevent the representation spaces of the different data types from collapsing into a single confused manifold. It explicitly decouples the processing of the three streams we just outlined: the video latents, the latent actions, and the executable actions.
So by routing these distinct modalities through separate expert networks, you preserve the unique mathematical properties of each representational space.
Exactly.
Now, if you are currently trying to wrangle gradient interference in your own multimodal setups, pay close attention to Level 2 here, the action level MOT. Because decoupling modalities is good, but Level 2 is where they actually stop the base mobility and the arm manipulation from destroying each other's weights.
Right. The action level motif strictly decouples the executable action stream itself. Instead of a dense layer trying to output both wheel velocities and arm torque simultaneously, the MOTI architecture uses a gating network to dynamically route the tokens.
So when the task requires moving the mobile base, Those specific tokens are routed to a mobility expert subnetwork.
Yeah. And when the task requires manipulating an object, tokens route to a completely separate manipulation expert.
So mathematically, during backpropagation, the sharp, high-frequency loss signals generated from, say, a failed grasp, they only update the weights within the manipulation expert.
You got it. They are completely physically isolated from the weights calculating the smooth trajectory of the robot's base. The gradient interference drops to zero because the gradients are literally flowing through different neural pathways.
That is so clean.
And the gating mechanism handles the blending seamlessly at the output. This allows the network to specialize incredibly deeply in both physical behaviors without them ever fighting for dominance over the same parameters.
Right.
And the authors highlight that this decoupled framework means the core architecture doesn't have to fundamentally change whether you are deploying a single-arm wheeled robot or a bimanual quadruped. The DMOT simply learns to route to the newly defined action subspaces.
It's a beautifully structured solution. Temporal alignment is fixed. Spatial and physical gradient interference is fixed. But we still have to cross the valley of death deployment.
Oh yeah, the hardest part.
How do we stop the model from collapsing the second it hallucinates a weird pixel during a 300-step long horizon task? They solve this exposure bias with a progressive 3-stage training paradigm that finishes with what they call dream forcing.
Yeah, so stage 1 is standard pre-training on large, diverse robot datasets to establish base visual and physical priors. It's stage 2, which they designate as Supervised Fine-Tuning 1, or SFT1, where the strategy gets really interesting.
Okay, what happened there?
In SFT1, they perform joint world model and inverse dynamics fine-tuning on the target dataset, but they still rely heavily on ground truth futures.
Hold on. Wait a second.
Yeah.
If teacher forcing relying on ground truth is the exact cause of the exposure bias that makes these models collapse, why are they explicitly doing it during the fine-tuning phase? Why not just rip the training wheels off immediately?
Well, you have to account for domain shift. Your pre-trained world model has broad general knowledge, but it is not yet adapted to the specific lighting, textures, and physics of your new target environment.
Right, okay.
If you immediately strip away the ground truth and force the inverse dynamics model to learn from the world model's initial, highly inaccurate predictions in this new space, those massive visual errors will fundamentally poison the action learning. You use teacher forcing in SFT1 strictly to stabilize the latent space and adapt the world model to the new visual domain.
I see. So you use the ground truth to calm the network down,
Yeah.
get it accustomed to the new room, the new objects, and then once the world model is generating reliable predictions, you pull the safety net. You unleash Stage 3, SFT2, dream forcing.
Exactly. In SFT2, the ground truth video latents are entirely removed from the conditioning. The model is forced to take its own autoregressively predicted visual rollouts, its dreams, and the inverse dynamics model must learn to derive accurate motor commands from those noisy, imperfect latents.
It perfectly mimics the exact mathematical conditions it will face during autoregressive inference in the real world. I mean, think about your own pipelines, kind of like training a pilot. SFT1, with its teacher forcing, is like putting a student pilot in a pristine simulator on a calm, sunny day.
Right.
It's strictly necessary to teach them the basic controls without them crashing immediately. But dream forcing is when the flight instructor starts throwing in realistic turbulence, sensor drift, and a glitching altimeter. The pilot actually have to learn how to interpret messy, corrupted data and recover before the plane stalls.
That is the exact causal mechanism happening in the weights here. By training on its own artifacts, the inverse dynamics model learns that a slightly warped pixel on a generated cup does not mean the cup has physically mutated.
Right.
And it shouldn't violently jerk the arm in response. The ablation studies in the paper demonstrate this beautifully. If you remove the dream forcing stage, the model's performance on complex, long-horizon tasks drops drastically because the compounding visual errors simply overwhelm the action space.
Which is fascinating. Okay, let's talk about the nightmare of actually training this architecture.
Yeah, it's not trivial.
Looking at a multi-stream, long-sequence joint video action model filled with latent intermediate layers and dynamic MOT routing as an ML engineer, I see a pipeline that is going to immediately throw out-of-memory errors and bottleneck my GPUs. How do they engineer this so it's actually viable to train?
So the paper outlines two vital engineering optimizations, starting with efficient structured attention. In a multi-stream model, you have a web of complex causal dependencies. Video tokens can't look at future action tokens. Action tokens must look at latent intent tokens. Typically, to enforce these rules, engineers apply explicit block masks over the full attention matrix.
Which is mathematically barbaric.
It really is.
Normally, attention mechanisms look at everything. It's like trying to read every single book in an entire library just to find one specific quote. Block masks are like taping over the pages of the books you don't need to read. It technically stops the network from reading them, but you still had to walk to the book, open it, and process the tape. You are calculating massive matrices just to throw huge chunks of the data away. For long sequences, it completely crushes your VRAM.
And to solve this, the AMAP CV lab bypassed the block masking entirely. They reformulated the attention mechanism by packing the valid query key ranges into contiguous segments using variable length flash attention. Think of it as physically moving only the exact untaped pages you actually need to a single small reading desk.
Oh, wow. So you are only allocating memory for the specific token interactions that structurally matter.
Yes, by treating the structured mask as a set of dense subproblems and dynamically packing them, they report a 5x speedup in the combined forward-backward pass compared to a standard flex attention baseline.
A 5x speedup is massive.
It drastically lowers memory consumption, making the massive sequence lengths actually fit in hardware.
I really want to emphasize this for everyone listening. When you are dealing with sequence models in robotics, optimization is architecture. If you cannot fit the batch size in VRAM, your brilliant theoretical alignment doesn't even matter.
Yep, it's just theory.
But memory is only half the battle. Repeatedly running raw video frames through an encoder during training is going to bottleneck your compute anyway. Did they find a way around that encoding tax?
They did, yeah, through a technique called offset-based latent augmentation. During training, extracting video features frame by frame is computationally prohibitive. So they pre-compute the video latent features at a fixed temporal stride, for example, grabbing every fifth frame. But if you use a rigid window that always starts at frame 0, your model overfits to that specific temporal segmentation.
Right, so instead of re-encoding the raw pixels every single epoch with a different starting frame to get variation, they randomly shift the temporal stride window over the already extracted latent features.
Exactly. It allows them to generate diverse latent segmentations and build temporal robustness without ever having to pay the compute cost of running the raw video encoder more than once. It massively improves data efficiency.
Okay, so we have the architecture aligned for time and space. We've cured exposure bias with dream forcing. And we've optimized the memory and compute so it actually runs. Let's look at the deployment benchmarks. Does this theory hold up on physical hardware?
The empirical results heavily validate the architecture. In simulation, they tested across Robocasa 365, which is the current benchmark standard for complex mobile manipulation in household environments.
Right.
ABot-M0.5 demonstrated significant gains specifically on long-horizon composite tasks. This proves that the temporal alignment and the dream forcing effectively prevent those compounding errors over extended timeframes.
But they also needed to prove that the action level motif was working, right?
Right.
If you optimize heavily for moving a mobile base, do you lose the ability to do highly precise stationary tasks?
Right, and to test that, they benchmarked on RoboTwin 2.0 and Libero. The model achieved highly competitive, state-of-the-art performance across the board. The low-frequency mobility routing did not wash out the high-frequency bimanual manipulation capabilities. The gating network successfully protected both skill sets.
Okay, but simulation is simulation. The true test of any embodied AI is deployment on physical hardware. They deployed this on an Agilex Piper arm, correct?
They did, and the physical deployment yields arguably the most critical statistic in the entire paper. They wanted to test the data efficiency of the fine-tuning process. So, for a highly precise, fine manipulation task inserting a peg into a cylinder, they gave the model only 50 real-world demonstrations.
50. Not 5,000, just 50 demonstrations.
With only 50 shots, ABot-M0.5 achieved a 96% success rate on the physical robot.
That's insane.
For context within the industry, the highly regarded 0.5 model achieved 90% under similar constraints, and FastWAM hit 77%.
Think about the economic implications of a 96% success rate from just 50 demonstrations. If you were an engineer tasked with building custom enterprise robotics for a warehouse or manufacturing line, the cost of human teleoperation and data collection is your absolute biggest bottleneck. If you can deploy a reliable, robust physical behavior with 50 demos, instead of spending weeks collecting thousands, you fundamentally change the economics of the entire robotics industry.
And the ablation studies clarify exactly why it is so remarkably data efficient. They fine-tuned a version of the model without their specific pre-trained visual and interaction priors. The success rate dropped by 31.2%.
Wow, you lose a third of your performance immediately.
Yep.
Which mathematically proves that the pre-training is successfully establishing deeply transferable physics and visual priors within those latent action spaces. The 50-shot supervised fine-tuning isn't trying to teach the robot what a cylinder is. It's simply adapting the existing conceptual intent to the specific kinematics of the Agilex Piper arm.
Exactly. It highlights the absolute power of decoupling the representation of intent from the execution of movement.
Man, that is so cool. Okay, to synthesize everything we've unpacked today on AI Paperslop, the secret to cracking mobile manipulation isn't just mindlessly throwing more unstructured data or compute at a vision language action model. It's about respecting the underlying physical structure of the problem.
Definitely.
You have to align the temporal resolution using latent actions. You have to explicitly decouple conflicting motor controls using a mixture of transformers. And you absolutely have to train the model to survive its own hallucinations by forcing it to learn from its dreams.
I think this leaves us with an incredibly important question about the future of this architecture, actually. We've seen how effectively the DMAT routes tokens to decouple mobility from manipulation. But consider what happens as we scale this framework from wheeled, single-arm robots to highly complex humanoids.
Wow.
Imagine introducing a third, fourth, or fifth parallel axis of continuous control.
You're talking about dynamic facial expressions responding to human interaction, precise binocular gaze tracking, or even swarm communication protocols outputting continuous signals to other robots.
Yeah. As you add infinitely complex parallel action spaces, will the mixture of transformers architecture scale seamlessly by simply adding more expert networks? Or will dividing the physical outputs into rigidly separated mathematical silos eventually fragment the model's holistic understanding of its own body in the physical world?
That is a fascinating and slightly terrifying thought for anyone working on full humanoid deployment. Because if we force the network to use completely isolated pathways for every single physical subsystem, do we inadvertently lose the ghost in the machine?
Right, that emergent fluid coordination that makes biological movement so seamless.
It is definitely something to think about as you design your own ratting architectures. Thank you all for joining us for this deep dive into the AMS CV Lab's latest work. We highly recommend you pull up the full paper and study their attention optimizations over on their GitHub. Until next time, keep your temporal granularity aligned and your action spaces decoupled.